So this is mainly the Manfred's brainchild, this talk, this work. So he's the main author, but he's not here, so I'm going to give a talk. So it's about rotation invariant algorithms not being learn sparse targets optimally. So this is a previous result in the under constraint case. So under constraint case, we mean like the case where the number of examples is less than the dimension. So we have like a very simple setup where we have this matrix H, which is a Hadamard matrix of plus minus ones with orthogonal rows and columns, and then instances are just the rows of this matrix. Then we have this sparse target vector, weight vector, in this case E3, and the labels are simply generated by this simple linear model. Algorithm receives less than the examples, and it's supposed to predict labels on the remaining examples, and then it's evaluated on the entire set of the examples by the average squared loss. And well, this is results for two algorithms. One is gradient descent on the left, the other one is exponentiated gradient on the right. And this on the x-axis we have number of examples seen. On the y-axis we have the red curve is just the error. So as you can see, the error for gradient descent decreases linearly down to 0. Quite slowly, it's essentially 1 minus n over d after seeing n examples. And this means that the algorithm doesn't really learn anything about unseen examples. This is the average of the entire set. On the other hand, on the right-hand side, you see that EGU learns much faster. The error decreases as 1 over n, essentially. And also, these are weights plotted in blue. And that's the weight that corresponds to this sparse target. So it goes to 1 slowly for GD, and it goes much faster to 1 for EGU. Similar results are obtained for random plus minus 1 matrices rather than this structured Hadamard matrix. But anyway, it shows that GD doesn't work here. Actually, EG works better, but you don't need to change the algorithm. You can actually stick with gradient descent and change the simply change the model by using this type of two-layer linear net, which Manfred calls spindly network. And the idea is that you have essentially one parameter here, and then there are no interconnections between these nodes. So like the model is very simple. It's just a sum of products of these parameters. And then it turns out that running gradient descent on that simulates exponentiated gradient. So these two plots are essentially almost identical. So you can stick with gradient descent and solve these type of sparse problems more efficiently. So those are, I'd say, still results from the previous work. Well, it happens that it's not only gradient descent, but also any rotation invariant algorithm that has problems. So algorithm is rotation invariant if its predictions don't change if we rotate all data by some orthogonal matrix. So including input data, like training data and test data. So there are like many models which are rotation invariant. For example, all linear models with L2 regularization, neural networks with fully connected bottom layer trained with GD, and apart from that, arbitrary, like with arbitrary depth, non-linearities and structure. And we also showed that any rotation invariant algorithm has exactly the same bad behavior as gradient descent on this Hadamard problem. Well, with some modifications to let's say, cover like a larger class of algorithms. Okay, so, well, who cares? I mean, in most cases, we have more examples than dimension, and all previous bounds become vacuous when the number of examples is larger. So the contribution of this work, finally, is well, in the over-constraint case, when the number of examples is larger, these rotation invariant algorithms will still perform suboptimally by a factor of d dimension when we just add noise to the targets. So this is the model we are considering. This is the labels are this linear model plus this Gaussian independent noise. This X matrix is still a matrix of orthogonal rows or a matrix of instances generated from some rotationally symmetric distribution. And the algorithms are then evaluated by their excess risk relative to this sparse target EI. This test example is again one of the rows from X or drawn from the same rotational symmetric distribution. And what we show that there's this lower bound for any rotation invariant algorithm, which is essentially when we assume that the noise rate is fixed, it depends like d over n. So clearly the error decreases to 0, of course, because we get more and more examples, but it doesn't decrease like optimally fast because we can get rid of this d factor. So the proof is essentially by a Bayesian argument. The idea is that you put, essentially you do some arbitrary rotation of the entire problem. Then you could have a prior over these rotations. And the rotation invariant algorithms, they need to behave exactly the same for every type of this rotated problem. And there's an optimal algorithm with this prior, which is base optimal. So we lower bound the risk of the base optimal algorithm. And this is also a bound for any rotation invariant algorithm. But there are algorithms which break this bound because they are non-rotation invariant. So in particular, exponentiated gradient, and also the Spindly algorithm. So if you run them with early stopping, which is crucial because otherwise they would eventually converge to least squares or ERM solution, the error decreases as log d over n, which is like d over log d faster than rotation invariant algorithms. So there are like many technical details about this proof, which can be found in the paper. We also showed that there's this new algorithm called primed GD, which I'm going to talk about later for a moment, which doesn't even have this log d factor. So it's even better, and we conjecture that none of these algorithms have this log d factor in this problem. And well, similar up and bounds with this log d factor can be found in the literature for lasso. So we also analyzed the gradient flow trajectories. So because our problem has quite simple structure, we can actually go to continuous time, get this gradient flow differential equations, and actually solve them analytically. So this is what we did for various algorithms. So what are these plots here? So these are like this gradient descent, this primed version of gradient descent, EGU, and also Adagrad, for instance. And we have like 2 dimensions, so we have 2 weights. And this green dot is the optimal solution. It's vector 1, 0, right? So this is like the sparse optimal vector. Then all algorithms start from 0, 0, which is here. And then we look at their trajectories. These black points are least square solutions or ERM solutions to a bunch of randomly generated training set with a fresh copy of noise each time. So obviously, if we run the algorithm long enough, they will all converge to a least square solution. But the trajectory is very different. So for gradient descent, it just goes straight to these solutions. But if you look at prime GD or EGU, they actually follow this sparse line here. So they get very close to the optimal solution. And only at the very end, they bend towards the least square solution, which means that if L is stopped, they will just get much smaller error. Adagrad has the opposite bias, actually. It's biased towards dense solution. We also did the same experiments for larger dimension. In this case, we cannot show weights, but we can actually decompose the total error. So it's in 256 dimension, total error into 2 parts. One, let's call it signal error. It's like the error parallel to the target weight vector. And then the noise error is the remaining part. This is orthogonal or perpendicular part of the error. So then we can look at the algorithms, what kind of error do they decrease first. So here we have a sparse target, and we also look at the dense target. So here on the bottom right, that's a starting point for each algorithm. And then this red dot here is the optimal place with 0 error of both kind. And this is this black dot is a least square solution. So all these algorithms go towards least square solution, but these 2 lines here, they correspond to primed GD and EGU. So as you can see, they go very close to the optimal solution. Only at the very end, they go to the least square solution. This is because they essentially learn signal first and noise only at the very end, while actually this is Adagrad, it does the opposite. But situation changes for dense target. Now, for dense target, EGU learns noise first and signal next. So since it's a fashion week in Milan, it's good time for a fashion eminist experiment, which we were all waiting for. So we actually did experiments on real data here with a fully connected network with 2 hidden layers. One, like I would say, standard fully connected layer and network, and then one with this additional layer here, which is like the spindly network layer, put right after the bottom after the input. And we looked at how these two behave on this MNIST data set. So we have like original features of the images, and then we also have noise features, which is essentially pure noise at the same number as the number of original features. And then we also have the third type of features. We call them informative, because this is like one hot encoding of the class vector, which means that these informative features is essentially the output, which is concatenated to the input. So with only image features, both architectures, they get the same type of error, 85% of accuracy. With noise features, this spindly network retains the original accuracy, while the accuracy of this fully connected network drops down. And well, with informative features, the problem becomes super easy because we have output at the input, which means that we should expect every algorithm to get 100%. But actually, this fully connected network is not reaching 100% because of the noise. So just to sum up, well, for noisy sparse targets, rotation invariant algorithms are still suboptimal when the number of examples is larger than dimension, because noise keep rotation invariant algorithms away from sparse target. And we also found this surprising new priming method that I already mentioned that achieves sparsity. So this goes like this. We run gradient descent for a moment, and then we actually transform instances by multiplying instances. This is like coordinate-wise multiplication by the weight vectors, and then run GD on those instances for a bit more, and that actually works very well for sparse targets, because this middle step, it breaks rotation invariance. The remaining steps are rotation invariant, but this one that is not. And like the take-home message is to, it seems important to understand the biases of all common optimization algorithms. So that's it. Thank you very much.
Any questions?
Can you say a bit more about why this priming methods, what the intuition is?
So I think it's a bit like multiplicative update then. I guess that's the idea, but you can also write it down as a problem with a regularizer, and it turns out that it's like a squared regularizer, like in gradient descent, but the regularizer depends on the solution. I think a regularizer is like it's a diagonal matrix with inverses of the weights or squares of the weights in this matrix, which means that those directions for which the weight is small will have much more penalty. So the algorithm will not going to like increase weights along these directions.
Thanks.
It's a bit like L1.
Yes, I'm quite familiar with this work, of course, but I was going to ask you, is there an algorithm or an idea for an algorithm that would be agnostic to whether or not the best solution would be sparse or not, and that essentially would preserve good properties in both cases?
Oh, yeah, that's a very good question. So we don't have one. Seems like there is always some kind of inductive bias that might hurt you when the problem is not, let's say, sparse. But yeah, that's a very good question. Maybe there's a way to adapt without losing that much. You know. Thank you.
These were pretty interesting plots you had of like the different optimizers and how they, you know, the trajectories and stuff. I'm wondering if you have any, is it just experiments? Do you have any theoretical explanation as to like the different biases for, say, Adagrad and stuff?
So we could compute like closed form analytical like trajectories for these algorithms. But for the explanation, I think just gradient descent simply goes along like the straight lines here is because it is rotation invariant.
Right. But for the other ones?
Yeah, for the other ones, well, they have like strong bias towards sparsity. So
sure.
I think we're just going to stay close to the solutions for which let's say one of the weight vectors, one of the weight coordinates is close to 0. So I think that's why
Sure.
they are moving along this
But
direction.
how about Adagrad? That's, I guess, the least intuitive one for me.
Yeah, so this is actually diagonal Adagrad. I think
I see.
the Adagrad, which the original Adagrad was this type of matrix based, and that would also be rotation invariant. But for this one, honestly, I don't really know.
Okay.
That's a very good question.
Cool. All right.